importance level of the effect size, and by that we could know that if this effect size, if it's important or no, if it's
Yes,
below or above the importance level. Yeah. And then in the
correct.
previous lecture, yeah, in the previous lecture when we calculated the effect size, we didn't have that importance dashed red line. So how could we know that this effect size is important or no?
Yeah, I think you'll need to, I'm not sure which slides you're talking about. The IQ example?
The No, yeah, the exercises that we did, the calculations and the exercises that we did the last time, we calculated the effect size also by jamovi, but I didn't get how could we decide if it's important or not.
Oh, I see. Well, yeah, we can't decide if that's about. We need to be an expert in whatever the measurements are. So the example I gave was, let's say, blood pressure changes. If it's going to be any use as a drug that reduces blood pressure, then what are you talking about? Are you talking about 1 millimeter of mercury, or 5 millimeters of mercury, or 10? I don't know. So the expert might say, okay, well, actually for the drug to be beneficial, we need it to be at least 10 to reduce blood pressure by 10 millimeters of mercury. So it is an expert call. So that would be the effect size that would be useful, or the minimal, clinically important effect size. How you work out the actual effect size from the data, well, that's just going to be, if you're dealing with measurements, it's going to be the mean effect or difference divided by the standard deviation. Is that any good?
Okay, yeah, okay, yeah, okay. Thank you, doctor. But I have another questions.
Okay.
If we yeah, when we calculate the t value for the previous lecture, do we always use the degree of freedom instead of n?
Yes, you always use degree of freedom for T. Yeah. When you report
And I'm sorry, doctor, but what?
when you report a T value, you give the degrees of freedom. Yes. Why?
Okay, doctor. Yeah, thank you, doctor. But I have sorry, but third question.
Okay.
I don't get. Yeah, sorry for
Yeah.
that.
Carry on.
I
No,
don't get
fine.
the point of calculating. Yeah, I don't get the point of calculating the paired related analysis. Is it the is it like we just want to shorter the questions, or the no shorter the steps that we are taking in doing the analysis? So we just want to like um, do like a list steps in the analysis.
Well, we wouldn't be working it out by hand. Is that what you're Is that what you're talking about? I mean, with the paired samples test, you basically look at the pairwise differences, okay? And then you test those differences, okay? That's if you were to do it by hand. But in jamovi, you just put in those two columns, and it's in the paired or related samples test. And then it does the subtraction for you and works out the one sample t-test on the data.
Yeah, but what I don't get is the point of calculating the paired related analysis.
The
Is it?
differences?
Yeah,
Well,
what's the
because,
point? Like,
okay, the point is the example that I gave you, which comes from Gossett's paper, was for two drugs, okay? And these two drugs were given to the same patients. So what you can get from this analysis is whether drug A and drug B are different in their effectiveness to prolong sleep. Is one more effective at increasing sleeping time compared with the other? That's what you get out of it. If you just look at each of the columns of data, then you're basically just seeing whether that drug is different from 0. When you do a paired test, you're seeing whether the difference between drug A and drug B is different from 0. So there are different questions that you're answering.
So like we don't compare each individual drug with the null hypothesis. We
Well, we
compare
did.
the two drugs.
Yeah, you can. I think I did that. The one sample test, you look at each of them on their own. So is drug A, does it affect sleep? Does it increase it or decrease it? We found, I think, drug A didn't do much. Drug B, there was an increase in the amount of sleep. And then when you do the paired test, what you're testing is whether drug B is significantly different from drug A.
Yeah, I got it. Thank you so much, doctor.
Okay. Any other questions? Okay. So you can see the screen, right? And I'm just going to go through, this is a quick test. So if you've got an independent samples t-test, each person acts as their own control across different conditions. Or B, there are different participants in the 2 treatment groups. Or C, the same participants are in the 2 treatment groups. So this is independent samples test. So yeah, everyone is, well, 2, 3, everyone's saying B, correct. Okay, the t-value is calculated in a t-test by dividing the difference in means by the population standard deviation, the sample standard deviation, the standard error. Yes, again, everyone's getting this right. It's C. Good. Standard error. It's not the standard deviation. It's the standard error, which takes into account the size of the sample. Okay. The null hypothesis tested by an independent samples t-test is that the 2 population means are identical, the 2 sample means are identical, or the 2 population variances are identical. Which one? This is a trick question. And, okay, any more responses? Okay, only one correct. A is the right answer here. We are testing population means. The trick, why you got tricked, is that we use the sample means to do the analysis, but we are making an inference about the population means. Okay. The advantage of the before-after related samples design is that there are order effects. The variability between participants is removed from the analysis. Finally, there is homogeneity of variances between the groups. Okay. All right. Any more responses? Yeah, okay. People are somehow getting in trouble with this one. This is a related sample, so paired samples design. If you've got before and after, then one of the problems is order effects. So that is not an advantage, that's a disadvantage. So A is definitely wrong. C does not apply to the related samples design because that is when we're dealing with 2 independent groups. So by elimination, although B is the correct answer, no one seems to, okay, one person I think got it. It's the variability between participants which is removed from the analysis. Because we're using the same person, they act as their own control. So you remove the variability. You've got 2 measurements from each person. So we can remove the variability between different people, which is nice. So B is the answer for the last question. C would not be the right answer if you're dealing with I mean, homogeneity of variance is an assumption. It's not an advantage. It's just an assumption that we can make if we want to do a t-test analysis. However, I've told you, I've encouraged you to use Welch's version of the test, which does not require you to assume homogeneity of variances. So I think it's safer to actually use Welch's test rather than do the normal t-test, which assumes homogeneity of variances. Okay, so today and tomorrow I'm going to be talking about analysis of variance, just one-way independent groups, analysis of variance. This is the simplest type of analysis of variance. There are other ones where you've got related participants or repeated measures, and also where you've got more than one factor. So we're doing a one-way or one-factor analysis of variance. I'm going to be going through the basic logic, the conceptual basis for the test. I'm going to give an example, and tomorrow I will be dealing with multiple comparisons. Like a t-test, but it's an extension of the t-test, so that you can test any number of means. When I say any number, it means, 100 if you wanted 100 different means, 100 different levels of one factor. Okay, so basically what it does is it compares variability between the groups, between the different groups. Let's say we only had 3 groups and we wanted to compare the scores in those 3 groups. It looks at the variability that we see within each of the 3 groups, and also the variability that there is between the groups. So how the group means differ. And that's how it tests the differences between the means. I'm going to explain this a bit more. Let's just think of these sampling distributions for 3 means, and they're centered on 3 population means here. Okay, these are the sampling distributions. This is for the blue mu1, this is for mu2, and then this is for mu3. Okay, so now the population values are shown by the mu's, mu1, mu2, mu3, and this shows one particular scenario for an alternative hypothesis that is true. So what other alternative hypotheses might there be? This one, it tells us that mu1 is less than mu2, which is less than mu3. You can see that they are in different places on this axis, going from low to high. So can you think of any more? If we just had 2 means, we would say, okay, mean 1 is less than mu2. An alternative would be mu1 is greater than mu2. Okay, those would be alternative. There's only 2 alternative hypotheses. What about if you've got 3 means? Well, it becomes a bit more complicated. What you can have is, okay, you can reverse it. You could say that mu3 is less than mu2 and less than mu1. That's just a simple reversal. Or you can mix them up a bit and say that mu1 is greater than mu2 but less than mu3. You could also say things like mu1 is equal to mu2 but less than mu3. Mu1 is equal to mu2 but greater than mu3. And so actually there's very many different alternative hypotheses. What about the null hypothesis? Does anyone want to volunteer what the null hypothesis is here?
Can I answer? I think it's mu1 is less than mu2 is less than mu3.
So what I'm showing here, that you're saying that's the null hypothesis?
I think so.
I've told you this is an alternative hypothesis, so it's not a null hypothesis. This, what I've shown you here, is an alternative. Okay, someone has written that there is no difference between the means. This is the correct answer. It's when these three means are exactly the same. That is the null hypothesis. And there is only one null hypothesis, okay? So mu1 is equal to mu2 is equal to mu3. Okay. All right. Now, we can measure variability in terms of variance, and we get that variance in two different ways. If we've got three groups, for example, we can look at the variability within each of those three groups, okay? And we can get an estimate for the variance. So there's the within group, we're talking about within group variability. It's how the numbers within each of those groups differ from the group mean. So there are going to be three group means if there are three groups. And within each group, we're looking at the data points and how they vary from the mean for each of those groups. So why do they vary? Well, they vary from their mean because of individual differences, and also there may be errors, okay? They're going to vary a bit. Everyone gives a slightly different score. If you're measuring height or something, it's going to be slightly different heights. We also can get variability from looking at how the means of the three groups differ, okay? Now, by sampling variability, we would expect the three means to be a little bit different, okay? It depends how large the samples are and so on, but we wouldn't expect them to be identical. Even with the null hypothesis being true, there's going to be some variability if we're talking about a proper measurement variable like height or weight, or some constituent in the blood or something. It depends, you know, if it's something that we can measure quite accurately, there's going to be some variability. Now, this difference between the groups, this is the between group variability. So how do the means differ? Well, again, this is due to individual differences. They will contribute to that difference, and also errors of measurement. So just like we had before, but also when there's a treatment effect. So if, let's say, treatment 1 gives higher scores than groups 2 and 3, then that will make the differences between the means, the sampling variability will be different. They will be higher, be larger differences. Whereas if the null hypothesis is true, then the treatment effects will be 0, basically. There's no treatment effects. So just looking at these together, we've got the within group, which is how the data points within each group vary in the three groups. And then we've got the between group variability, which is how the three means differ from each other. How variable are they? Now, if there are no treatment effects, if the null hypothesis is true, then this disappears in the between group variability. This is 0, okay? And that means that we should then be left with two estimates for variability which are the same because they're looking at the same things, individual differences and errors, whatever they are, errors of measurement. If we're looking at these two estimates of variance, if the null hypothesis is true, that is treatment effects are 0, then these two estimates should agree with each other. We get these estimates in different ways. So I'm going to run through this. Okay, so the within the S squared, this is the within groups variance, is based on the variability within the groups, and it's independent of whether or not H0 is true. That is because it's only looking at the variability of the points within each of the groups. It doesn't actually look at the variability of the points relative to other data, the other groups, or the other means. It's only within each of the groups. In contrast, the estimate that we get for the between variance, so this is S squared B, this is for the between groups variance, is based on the variability between groups. And this value is affected by whether or not the null hypothesis is true. So if the null hypothesis is false and there are differences between the means, then this estimate will be large, okay? If these estimates are similar, as I showed in the previous slide here, where there are no treatment effects, if the null hypothesis is true, then these two estimates should actually give you the same number, similar number. Okay, so if the between groups variance is much greater than the within groups variance, then there must be some group differences, and that contributes to this S squared between, and we should reject the null hypothesis. It suggests that the means are different from each other, more than we would expect by chance. So I'm just going to go through a scenario where the data has been made up conveniently. So where we've got this data, group 1, group 2, group 3, and the means here, you'll see 6.33, 4.33, 5.33. This is where the null hypothesis is true, okay? So these differences in the means are just due to sampling variability. Since the null hypothesis is true, actually, these means do not represent true differences. You can see the plot here with the 95% confidence intervals. They include that each of the means is included within the confidence intervals. And you'll see that the variability, the variance within each of the groups has been contrived so that it is identical in the three groups. So it's actually 10 for these numbers, again 10 for these numbers, and 10 for these numbers. So this is the within group variance is actually identical, but you'll see there's some differences here between the means. But I've told you the null hypothesis is true. So let's work all of this out. We've got a grand mean here, which is conveniently in the middle between 4.33 and 6.33. So that's 5.33. There are three groups, so we would say K is equal to 3. The number of scores in each group is 9. Now the sampling variance between the groups is going to be each group mean, take away the grand mean, squared, added up and divided by K minus 1. So if we go through this, we can do this very easily. We get 1, but I'm just going to go through it. So the group mean, first one here is 6.33, take away 5.33 gives us 1 squared. And then we do the next one, which is 4.33, take away 5.33 is minus 1. When we square that, we get 1. The last mean is 5.33, take away 5.33 gives us 0, so that disappears. So we've got 1 plus 1 is 2, divided by K minus 1 is 2, which gives us 1. Okay, so that's quite straightforward. Now, the between group variance we get by multiplying the sampling variance, which is what we've got here, 1, by the number in each of the groups. So there's 9 observations in each group. So it's going to be n times sampling variance. How did I get this formula? Well, it actually comes from something that we've seen before, and that is when I talked about the central limit theorem, the variance of x bar, so the variance of the means, okay, is equal to the variance divided by the sample size. If you remember, I said that the sampling variance was inversely related to the sample size. So if we multiply both sides by n, then we get n times the sampling variance is equal to s squared, and it's s squared that we're interested in. Okay, so that's the variance. So it's an estimate of the population variance. So what we do then is multiply this 1 by 9, it gives us 9. Now what about the variance, the within group variance, so the S squared W, well, that's very easy to do. I've made it so that these are all 10. And if you just add them up, 30, and get the average of them, you get 10. Okay, so you'll see that these two estimates of variance are pretty similar. Okay, how am I going to compare them? I could subtract them, or I could, what else? Any ideas how one might compare these two numbers? Okay, what we do is we take a ratio. So we take the ratio of the sampling, the between groups variance divided by the within groups variance. Okay, so it's going to be 9 over 10, which gives us 0.9. Now, if the null hypothesis is true, we would expect our ratio to be close to 1. Now, this is pretty close to 1. It's slightly less than 1. But anyway, it's close enough to 1. We can work out a probability. This would give us a large p-value. But I'm just going to tell you at this stage that this would not be statistically significant. Let's move to the situation where the alternative hypothesis is true. Okay, so this actually looks the same, but I've messed up with the means. So I've added a constant here. I think I've added 2 to these numbers. So if you go back to the previous slide, yeah, I've added 2 to each of these numbers. So it's now goes from 6.33 to 8.33. Okay, otherwise these two are the same. And I've just added a constant to these numbers, so the variance will remain the same. Okay, so the variances are still 10 across there. So I just do the same calculations. The grand mean is going to be the mean of these means, okay, which is 5.67. We've got 3 groups, we've got 9 in each group. Let's do the sampling variance. Now, I can't do this in my head, it's slightly difficult, but if you've got a calculator, you can do this. Basically, it's 8.33, take away 5.67 squared, added to 3.33, take away 5.67 squared, and then this one, final one, 5.33, take away 5.67 squared. When you add those 3 terms together and you divide by 2, you will get 6.33, but please check it. So we've got 6.3. What did we get before? It was quite a lot less, wasn't it? It was only 1. So you can see, because there's a difference in the mean here, this bumps up this, this value here. But we now need to get our between group variance. We need to multiply again by the number of observations in each of the groups. So it's going to be 9 multiplied by 6.33 gives us 57. Okay, the average variance within the groups, cunningly this remains the same. Actually not so cunningly, simply because if you add a constant to these numbers, the variance remains the same. So this is just like the previous slide. It's just the mean has changed, but the variance will stay the same. Okay, so the average variance is just those 3 10s added together divided by 3 gives us 10. Okay, so now our F ratio, F comes from Sir Ronald Fisher, who devised this technique, I think in about 1925. So we get our F ratio of 57 divided by 10, which gives us a value much larger than 1, 5.7. In the previous slide, our F ratio was 0.9. And here, if we were to put the data into jamovi and do the analysis, this would come out highly statistically significant. Okay. Are there any questions?
Doctor, there are a couple of questions from where the from a couple of slides ago.
Okay.
What do you mean by treatment effects?
Treatment effects is, does the treatment have any effect? If we've got 3 groups, let's say, as we do here, and they are, let's say, 3 different drugs, are the drugs having different effects from each other? The null hypothesis says no, the drugs are either doing exactly the same thing, maybe making everyone a bit better or a bit worse or whatever, or they're doing absolutely nothing, but they're having identical effects. In other words, their means are identical. That's the null hypothesis. And a treatment effect is that if there isn't a treatment effect in one of the groups, then it would increase or decrease their response, their mean response, compared with the other two groups. Now, as we've got three groups, it's a bit more complicated. So it could mean that two of the groups are the same compared with a third group, or it could be all three groups are quite different from each other. Okay, so so when we're doing an analysis of variance, we're looking at two or more treatments differing. Okay, you got at least one that is different from another. So it's two groups, at least two groups that differ from each other. That's what's meant by a treatment effect, if you like. Is that any good?
Another question that was asked a couple of slides ago is, what exactly do you mean by individual differences?
Individual differences. Okay, it depends what you're measuring. If it's, say, you know, blood pressure or something, you know, in a certain situation, okay, you may, a group of patients may be suffering from high blood pressure, okay, and you want to treat them, but when you measure each of these patients, you're going to get slightly different results, okay, so that's because of individual differences, okay.
Right. Some of the questions about the slides are some people.
Okay,
People
so
are
someone's
asking,
asked, yeah, is that in the chat? Is that what you're looking at?
yes,
the chat?
doctor. Yeah.
Okay, I'll just, someone's asked this question, how far away, exactly how far away from f is equal to 1 do we reject the null hypothesis? It's a good question. This depends upon the degrees of freedom. It depends on 2 degrees of freedom, actually. One of the degrees of freedom is to do with the number of groups. And we've got 3 groups here. So the degrees of freedom for groups would be 2. So it's a group, it's k take away 1. And then there's another degrees of freedom, which is going to be the number of patients in the study take away the number of groups. So here we've got 9 in each group, 9 3 is 27. Take away 3 would give us 24. So there'd actually be 24 degrees of freedom for the participants or patients. And then there's a calculation, or you can look it up in a table, but Jamovi does it for you automatically. It takes into account these 2 degrees of freedom, one for the number of groups and the other for the number of patients. And then it calculates whether the value is large enough. So yeah, so as I say, if you've got a small number, it's a bit like the t-test. It's just like the t-test, actually. If you've got a small number of participants in your study, then you need to have a larger F value for it to be statistically significant. If you've got a huge sample size, lots of patients, say 100 or something, then to get significance, you probably only need 2 point something to get significance. I'm just trying to think what it would be. 3 point something. It's going to be probably 3 point something. I can't remember from the table. You don't need to know the table. It's not like the Z table. It's different because we've got 2 degrees. It's not like the T table either. Okay. What else? How did we get 6.33? 6.33. That must be in the previous slide, right? Let's have a look. 6.33. Is that this 6.33 here for the first mean? Well, that's just when you add these numbers together and divide by 9, you will get 6.33. You can try that in Excel. The slides are up on e-learning, so you can just copy these numbers and put them into Excel. The last slide. Okay, let's see the last slide. Where's 6. This 6.33. Right, 6.33. Right. Okay. Well, that comes from. Happens to be the same number. It's not the same number, but it's got in a different way. Okay. So what it is this formula here. So it's going to be the sum of the differences of each of the means from the grand mean squared and then divided by k minus 1. So I told you can do this. I couldn't do this in my head. Some people might be able to, okay? So the first one is going to be 8.33, take away 5.67. Whatever you get with that, you square it, write it down, do the same for this mean, do the same for the third mean, add those three squared differences up, divide by 2, and you will get 6.33. Okay? Okay, good. Any other questions? Did I miss any?
Someone was asking what 57 is.
The what? 57. 57 is the between group variance. It's the estimate for the variance that we get from looking at the differences between the means. Now, if the means don't differ very much, we should get a value that is close to 10, okay, which is what we got when the null hypothesis was true in the previous slide. But because this first mean for group 1 is quite a lot larger than these other means, that increases, it inflates the between group variance. So it is now 57, whereas before it was only 9. Okay. Okay, getting some more questions. Can't keep up with this. One last thing, hang on. Okay. Okay, so Bushra is asking, why did we get this huge difference in the sampling variance and between group variance? Okay, I think I've answered that question. Yeah, that's because this mean differs so much. And when we look at the difference between 8.33 and 5.67, we square it. And when we also add those squared differences for the other two means, we get 6.33. Please check the calculations, okay, just to satisfy yourself. You can easily do this. And then, as before, we multiply by 9, and we get 57. In the previous slide, where the null hypothesis was true, these squared differences added up to 2, divided by 2 gave us a 1. And when we multiplied by 9, we only got 9 here. So the ratio was 9/10. Okay. Understand the null hypothesis. Okay, so the null hypothesis. The null hypothesis is a very, okay, it depends what you're interested in, but here we want to know if one or more of these treatments given to the three groups are effective. They may increase illness or decrease illness. We want to know if the treatments have any effect. Now, the analysis of variance is a general procedure which just tells us that there are differences between the three means, okay? Relative to the null hypothesis. The null hypothesis is that there is no difference between the three means, okay? So we're taking, that means that these, if the null hypothesis was true, then these 3 sets of 9 numbers would be coming from the same population, okay, with the same mean in standard deviation and so on. That would be the null hypothesis. If a treatment has an effect, then it means that the numbers would be affected by the treatment, be larger or smaller, and that they would not all come from, these three groups would not all come from the same population. Okay, does that explain that to Sumaya? The null hypothesis is, I've mentioned it quite a bit. It's basically that there is no effect. It's the only hypothesis for which we know the actual value. It's here we were looking at mu1 is equal to mu2 is equal to mu3. So if we subtract, Okay, it's difficult to do with 3 means, but if we've got 2 means, which is what I did with the t-test, if you subtract 2 means, you should get 0. Okay, that would be the null hypothesis, that there's no difference between the 2 means. Okay. All right. Let's maybe go on a bit. So I'm going to use an example here, go through an example. We've got looking at different treatments for Parkinson's disease. There's a no therapy control, so these people are not given anything, basically, these patients. There's a placebo control, so these people think they're getting some sort of treatment. There's conventional therapy, which might be L-DOPA, among other things, for Parkinson's disease. And then there's some sort of new age therapy, I don't know, waving crystals around or something, to see if that can help patients increase their mobility. So we've got 10 patients in each group, and they've been randomly assigned to these 4 different treatments, okay? In the previous example, I had 3 different treatments. Here I've got 4 different treatments. Actually, we can have 5, 6, 10, even, as I say, 100 treatments if we wanted to. Very rarely do you see papers that are published with, say, more than about 5 or 6 treatments, but it's possible to do as many treatments as you wanted, different groups, to have as many groups as you wanted to. Okay, so there's 10 patients in each of these groups, and important to say that they have been randomly assigned in ways that I just, okay, I haven't described how to randomly assign, but there are ways using random numbers, random number tables to do that. Now the dependent variable, the thing that we're measuring is improvements in mobility measured after 6 weeks of treatment. And this is assessed by a physiotherapist who is blind to the treatment. So this is blinded, they don't know which patients have received which treatment. They're just assessing each patient to see their mobility, and they get some sort of score. Now, if they've got positive scores, that means their mobility is improving. If they get negative scores, it means that they are getting worse. So here are the numbers. No therapy control. Yeah, these numbers are quite small. They probably kind of quite near to 0. Some are negative. Placebo control, you may be surprised to see that actually placebos are quite effective. They can improve mobility in things, in some conditions. So Parkinson's disease is partly psychological. There is a psychological element. So if they think they're getting better, then they kind of can move a bit better. So there is a bit of a placebo effect here. Conventional therapy, so this is our drug treatment, for example, you can see that there are clear improvements here. We've got many of the scores in double figures. And then we've got new age therapy, which actually doesn't look too bad. There's quite a few that are in double figures. However, some are pretty bad. So remember, these are 10 patients in each, so we've got 40 patients here. Okay, there's different patients in each group. This is not a repeated measures design. This is independent groups design. Okay, so we need to make some assumptions for the analysis, that the participants have been selected at random and they are randomly allocated to the different treatments. The data in each group is normally distributed, and that the variances of the groups are equal. So the variances within each of the groups is similar. Actually, we don't need to make this assumption if we use an analysis which I'm going to show you, which is Welch's analysis. Like for the t-test that I showed you, if you use Welch's t-test, you don't need to assume that the variances are equal. Anyway, I will show you that. Okay, so using jamovi, what you do is you can do it 2 ways. There's using analyses, then ANOVA. which is like this one in the menu. Here's the analyses, and you drop down the drop-down menu when you click on ANOVA. So this one, or you can use the one-way ANOVA. So the one-way ANOVA is a simpler one, but it does allow us to do the Welch analysis, which the other one doesn't allow us to do. So yeah, maybe I will run through this in Jamovi so you can see it happening. So here's Jamovi. I've got the treatment here. NT stands for no treatment, PC is placebo control, CT is conventional therapy, and NA is new age therapy. So I need to organize it into two columns, one with all the scores in a long column, and a second column which indicates the group membership. Okay. So to do the analysis, I would click here, and I'll do this first one here, ANOVA. And the score goes as the dependent variable, and treatment goes as a fixed factor here. Okay, so this is the basic result. I can select the effect size. It tells me what proportion of the variability is explained by the treatment. I'll come on to that a bit later on. Okay, we could also do some assumption checks, which I mentioned. So there's the homogeneity of variance, which we can check. There's the normality, and the QQ plot is also looking at the normality. Okay, we can also do looking at, we can do a nice plot of the means. So if we copy this into the means here, then it'll do some plot down here. Here are the means plotted for us. So this is no treatment, placebo control, conventional therapy is the highest, and then new age therapy is also a bit high, but it's a bit higher than the placebo, but it's also lower than the conventional therapy. Okay, what else? I think that's all I need to show you. Let's look at the output here. We've got the sums of squares worked out, and the F value, which is the ratio of these two things, just like in the example I went through. So this is the between groups variance. We get that by dividing the sums of squares by the degrees of freedom, and then the mean square for the residuals. This is the estimate for the variance that we get from the within groups. So if we divide 216 by 10.87, we get 19.87, and this tells us that it is highly statistically significant. This is very different from 1. It would be close to 1 if these were similar, but they're not. The effect size is quite large. This is called eta squared. You can choose either of these, either partial or just eta squared on its own. Really, these are this is for when you've got more than one factor. We've only got one factor here, so you don't need to worry about it. Just use eta squared. So this tells us that 62% of the variability is explained by the treatment effect, which is quite a large effect. Is the homogeneity of variances test. What we can see here is that the p-value is much greater than 0.05. So that tells us that there is homogeneity of variance across the four groups. So the variances in the four groups is similar. There aren't differences, not like one group has got higher variance than the other. And there's a normality test here, and all of these p-values are much larger than 0.05, which tells us that the data is basically normally distributed, although these are not so useful tests because our sample size is quite small. It's only 10 in each. And this is quite useful. It's a QQ plot, which tells us how the individual points differ from where we would expect them to be according to the model, which is the means, the four different means. This should lie they should be close to this straight line, and they are. It's pretty good. Okay, let's go and do another test, which is the one-way test, which is the simpler one to do. You can only do one factor here. Let me just go back, actually, just go back to this ANOVA. You can see here that you can put in other factors here. You can put, you know, a number of other factors. So you could have a two-way or a three-way analysis. So this allows you to do more. This one-way ANOVA, there's only one grouping variable, so that'll be our treatment, goes in here. The score goes in the dependent variable here. Now, I'm suggesting that you use Welch's, so you don't assume equal variances, and I think that's probably the default. Now, you'll get slightly different F value here. Anyway, it comes out statistically significant. You can do this one if you want, which you'll get exactly the same as in the previous analysis. Okay, so we might want to have descriptive plots, descriptive table. We can also do the same test that we saw before, that we did before, but we don't need to worry about the homogeneity of tests because we're using Welch's test, which does not need that assumption. And actually get the same output as before. Okay. I think that's all I wanted to show you for this. Although when we're looking at this plot, actually there is quite a nice plot that we can do, which will give us scores. So it plots the individual scores as dots. So this is like a dot plot. It's called a dot plot. So that's quite nice. You can see how the individual scores in each group, so there's 10 of these dots in each group, how they're distributed. It's a kind of honest way of looking at the data. Okay, so that's how we would do it in Jamovi. And basically this slide shows you that first analysis. So I've selected eta squared here. I'm looking at the 3 assumption checks. I've copied over treatment to here, and we've got a marginal means plot with the observed scores and so on. So that's fine. Here's that plot. And if we do a one-way ANOVA, we select all of these additional statistics. We don't really need the homogeneity test. We can see the normality test comes out non-significant. This is much greater than 0.05. And here's our means plot. Here's our QQ plot for normality. These points are close to the line where we would expect it to be if the residuals, the differences from the means, were normally distributed. Okay, effect size. I mentioned effect size eta squared. How do we work this out? So we can do this manually. Of course, it gives it to us, but you can do this. You can see how we get this, and we get this from the sums of squares. So sums of squares are the differences from the means squared, the sum of them. Okay, depending on which mean you're talking about. If you're talking about the grand mean, you'll get the residuals here. If you're looking at the treatment, then you need to look at the 4 individual means, as I did in the previous example. Okay, so these two numbers here, these are the sums of squares. And basically we want to know how large this number is, 648.1, compared with the total sums of squares. Now, total sums of squares are going to be these two numbers added together. Okay, so it's the between group sums of squares, SS, divided by the total sums of squares. And that is, as I've written here, 648.1 divided by 648.1 plus 391.4. And if you do this calculation, you get 0.62, which is the same as what we got here in the Jamovi analysis. So this number will vary from 0 to 1. Okay. So how do we report the analysis? Well, we would say that there was a highly statistically significant difference between 2 or more treatment means. F with 3 and 36 degrees of freedom. Remember I said that there are 2 degrees of freedom which we need to think about. This 3 comes from the number of groups. Because there are 4 groups, you take away 1, you get 3. And then 36 is going to be the total number of patients. There were 40, right? And we've got 4 treatments. So 40 take away 4 gives us 36 degrees of freedom for the patients. And then the F number, the F ratio is 19.87. P-value a lot less than 0.01. Our partial eta squared is 0.62, which is our effect size. So we give the means here. You can see no therapy control is low, placebo is reasonable, conventional is the highest, and new age therapy is a bit higher than placebo, but less than conventional. We can then include this plot, this or another plot, maybe a bar graph, or whatever you want to use. This is what we had before. So I think that's all I want to do today. I'm going to finish off the lecture tomorrow. Maybe there are questions people have for what I've just covered. Okay. Okay, someone's asked, what does an F value signify? Well, an F value, it's a ratio of the between groups variance. It's the estimate that comes from between groups divided by the within group variance. So it's a ratio of variances. That's what an F value is. And the null hypothesis will tell us that the F value would be 1. Now, because of sampling variability, you will rarely get 1, but you will get a value close to 1. In the example that I gave you, we got 0.9, which is close to 1, right? It's slightly less, but it's close. Now, if there are differences between the means, what happens is that you will get an F value that is greater than 1. Okay, it'll go like 2, 3, 4, 5. What did we get in this example? Well, it was 19.87. So it's very different from 1, and the p-value was extremely small. So the probability of obtaining such large differences between 2 or more means, assuming the null hypothesis were true, is very, very small, less than 1 in 1,000. If the F value is high, then it means that okay, this is a good question. If the F value is high, this means that the variance is, the variance for the between groups that comes from the between groups. So the treatment effect. So the variance for the treatment effect is high. Okay. Now, it's an interesting thing you might want to think about. I'm not going to test you on this at all, but in my example, the null hypothesis was true, and we had an F value of 0.9 in my made-up example earlier on. What happens if you get an F value of, okay, you can't get 0, but you can get very small F values. You could get like 0.1. Actually, you can get, you could get 0 if the means are identical, okay? If the 3 means happen to be identical, that's when you get very small F value. And that happens when your means are closer than expected, given the data. And this happens when, for example, people make up data and the data is too good to be true. They are too similar, if you like. And there's a different way of analyzing that, but we're not worrying about that. It's just a kind of forensic statistics, if you like. Okay, any other questions? Okay. All right. Well, maybe I will finish that here. Okay, thanks very much. I'll see you again tomorrow. Tomorrow I'm going to have an assessed lab, so the lecture will be quite short, and there will be a lab. I'll be distributing the sheets, and it will be online as well for those that will be attending by Zoom. And then if you could submit your work online, that would be great.
Doctor, could you just clarify for the students that the in-campus group is supposed to attend tomorrow?
Yes, they are. Yes, it's just like previous weeks. So they will come along, and I will give them a printout of the sheet for them to do. They can hand in then if they want, or they can submit online. It's up to them. Otherwise, those who are attending on Zoom will have to submit online by a certain time by tomorrow anyway.
Great.
Tomorrow will be the deadline.
Great.
And I think that counts for like 5% of your grade, something like that. It's one of your projects, I think it's called. Okay.
All right.
Thanks very much. See you tomorrow.
Thank you, Doctor. Have a good day.
Okay. Thank you. Sorry.